Hi everyone. So I have made some change in our previous program. So if you remember, the type of this sum was not a normal long, it was atomic long. But right now I have reverted it back to a normal long. If you remember, I had said one thing that I had kept it atomic long for some safety reasons. So now let's make it a normal long and see what goes bad. So I'll just run this program for you. And upon running, we can clearly see that the output that we have gotten for sequential execution is different from concurrent execution. So that means there is some functional flaw with our code because sum itself is not being computed correctly by our concurrent program. And this is concerning. This is very, very concerning, right? Okay, so we will try to understand that why this happened. Okay, so guys, let me tell you one thing first. Whenever you write concurrent program, there are three major danger zones. Okay, so we are going to talk about the first and the most important danger zone for now. So for that, I'll take a very simple example. Maybe this code is a little bit complicated, so I'll take a very, very easy code. So we have a simple class called as number store that contains an integer x. So if you create an instance of it, x will be initialized to 0. And then you have a method increment, which increments this x by 1 unit. You also have a getter for x. Okay. Now what I have done is I have written a main method, as you can see here. And inside this main method, I have created an object of this number store. And we have seen that when we create an object of number store, the value of x inside it will be initialized to 0. Okay, so we know that somewhere inside the memory, there is a variable x, which is 0. Okay, now I have created two threads and the runnable I have passed to them is a worker. So I have named it worker. This worker, what it takes is a number store. So it is injected with the number store object that we created, and it contains a run method which simply runs a loop for 1 million times, and it invokes increment on the number store. So we can just take some time and think about what this worker is actually trying to do. You can just pause this video and try to understand what this is trying to do. So it's very simple. All that this worker is doing is it is calling increment function for 1 million times. So basically it will have added 1 million to the current value of x. Okay. Now let's head back to this main again. So we have two threads. And the interesting thing is both the threads have the same number store. So this number store variable is a shared variable for both the threads. Because this number store is a shared variable, so x, which is contained inside this number store, is also a shared variable for both of them. Because we have seen that at the end of the day, these threads are actually going to change that x. Because inside the worker class, the run method, it creates an impact on the x by invoking increment method, right? Cool. So now when you go back to this main method, you can see I have just launched these two threads. And now you may be seeing this join for the first time. So I'll tell you very briefly what is this join. So let's say our current thread launched thread 1 and thread 2. Now if our current thread wants to wait for thread 1 to finish off its execution, that can be achieved by calling t1.join. So when I call t1.join, main thread will wait until thread 1 has finished its execution. Similarly, it will wait, the main thread will wait until thread 2 has finished its execution. And after that, we will print the final value of x. So you might have realized by now that why is it that we are doing this? Why we are waiting? We are waiting because we want to print out the final value of x after thread 1 and thread 2 have finished their execution. So according to you, what should be the output over here? Can you just pause and think about it? Okay, so straight away what comes to our mind is that we have a worker and this worker is going to add 1 million to the value of x. And because we have launched two threads, so first thread will add 1 million and second thread will also add another million. So basically the output should be 2 million. So let's run this program and see what happens. Upon running, we are startled to see that the value is not 2 million, which it was expected to be. In fact, it is smaller than 2 million. Why this has happened? So you can actually pause the video at this point of time and think for the possible cause of it. Okay guys, this is a very important concept that we are going to discuss now. So let's understand it quite clearly. So guys, when we look at a worker, they are invoking increment method on the number stored. Now be mindful of the fact that the instance of number stored that is being shared across the two threads are the same. It's the same instance. So it's the same X which they are mutating, which they are changing. Now guys, if you look at this piece of code which is x++, or whether you call it x equals to x plus 1, then you may be feeling that this is a one-step thing, but this is not really a one-step thing. In fact, it's a three-step process. Now, what are the three different steps? Let me tell you. The first step involved over here is to fetch the value of x from the memory, whatever its current value is. So let's say at some point of time x is equals to 5, then the thread will fetch from the memory that x is equals to 5. The second step is to perform some computation. So here the computation is to simply add 1 to it. So I can say the second step is to figure out the value x plus 1. And the third and final step is to finally write that new value back to the memory. So it's a three-step process. Fetch, compute, write. You fetch the old value of x, then you compute something internally, and then after that computation, whatever result has been procured, you write that value back to the memory. These are the three things that happen. And now we understand how threads are scheduled. They are all scheduled in a random way, in a time-sliced manner on the CPU cores, right? So guys, let's say your thread 1 got scheduled at some point of time, okay? So it was your thread 1 that got scheduled. And when it got scheduled, the first thing that it did as a part of this operation was to fetch. When it performed a fetch, it saw that the value of x currently is 5. Now, immediately after this, a context switch happened and thread 2 got scheduled. So when thread 2 got scheduled, the first thing it did would also be fetch. And it would also see that the value of x is equals to 5. Now after that, let's say again a context switch happened where thread 1 got scheduled. So now thread 1 would do 5 plus 1, which is 6. And then it would assign to x the value equal to 6, right? Now thread 1 has done its 1 unit of addition. Now let's say it is thread 2 that came into scene. Now when thread 2 comes into scene, because initially it had read the value of x from memory as 5, so it would also do a plus 1 on this 5 only. And it would also assign to x a value which is equals to 5 plus 1, which is 6. So guys, what just happened? 2 threads ran. Our intention was to get plus 2 from the plus 1 and plus 1 activity that both of them were doing independently. But in reality, it did not happen. Why it did not happen? We have just seen that. So guys, this kind of scenario is very popularly known as race condition. So when does race condition happen? Race condition happens whenever we have a shared variable which is shared across multiple threads, and if those multiple threads are trying to mutate or change that value, then the race condition can happen. See, if there is a shared variable across multiple threads and those threads are not changing it, those threads are just reading it, then the race condition won't happen. But if those threads are mutating it, then the race conditions can happen, and most of the times they do happen. Okay, so this is the reason why we were seeing a different output than 2 million. So now that you understand this thing called as race condition, there is no way to avoid it by putting any other form of logic over here. Because guys, in order to avoid it, if you put any other form of logic, the race condition might end up happening on that logic also. So it's a tricky thing. It's a very tricky thing. So there is a well-defined way for handling this. And we will be talking about that. But for now, the most important thing to realize is that the first danger of concurrent code is race condition. And it happens when we have a shared variable which is being mutated by multiple threads out there. And guys, sometimes the code you have written, it might not be thread safe. So I have introduced this term called as thread safe. Thread safe means that the code that you have written is never going to be impacted by the 3 dangers of thread. So the first danger that we learned is race condition. So if you have a code where race condition is not there, then that can be regarded as a thread safe code. Although there are some other dangers also, which I'll be talking about in the time to come. But at this point of time, I want to tell you that if I rerun this particular code, then the output that I'll get will be something different. If you run it again, you'll get something different. So if you run it for multiple times, every time you will see that there is a different output that is coming up. And why that is happening? That is happening because the way in which threads are scheduled on CPU core is non-deterministic. Okay, so this race condition, it happens when context switch occurs. So thread 1 fetched, and before it could compute and write, thread 2 also fetched. So, the pattern in which these threads are scheduled, that would have an impact on the final result. And if that's happening an impact on the final result, that means our code is not thread safe. Okay, cool. A lot of the times what happens is that the code you have written might be suffering from race conditions, but you are not able to detect it because your CPU might have luckily scheduled those threads in proper fashion. So guys, who knows that maybe my CPU scheduled thread 1, allowed it to do fetch, compute, write, and then it scheduled thread 2, allowed it to perform fetch, compute, write. If it did not interleave the fetch, compute, write of multiple threads, then I would not have seen this race condition happening. So if I just go ahead and make a small change, let's say I do not run it for so many times, I run it just for 1 time from both the threads. So if you run it just for, let's say 2 times here, you're just running for 2 times. Let's start with 1 time. What is the output that you would actually expect to see? You would expect to see the final value of x to be 2, right? So if I run this piece of code, I can actually see that the final value of x is 2. So because here the data, not the data, but here the number of iterations were very small, so this race condition could not be detected only. But if you make it huge, if you make it big enough, let's say even 1000, you can very well expect to see that. So here we are again lucky to not see that. But if you run it multiple times, you will see that 1 out of certain number of times race condition would have happened. Okay, and you can see that right happening over here. So make your code thread safe. Make your code devoid of race conditions. But how to make that? We'll be talking about that in the time to come.